Hello dear students, today I am starting here a chapter on electrostatic potential and Gauss theorem. The basic outline of the chapter is which I will cover are line integral of electric field, equipotential and potential difference, electric potential due to single point charge, group of charge and electric dipole. Then I will come to the points equipotential surface and its properties. Then we will derive expression for the electrostatic potential energy, area vector, solid angle and electric flux. Then Gauss theorem and its proof will be covered in this presentation. So now I start the presentation with work done by electric field, the line integral of electric field, and the line integral of the electric field is defined by this expression E vector dot dl vector integral from point A to B. The total work done by the electric field on unit positive charge in moving it from one point to another point in the presence of electric field. So here we are starting the expression from this diagram. Here we have plus q charge and here we have test charge q naught. We are moving this test charge from point B to A and then A to B and then calculate what is the work done. As we know, the work done is defined as the line integral from a point A to B E vector dot dl vector. This point A to B represent the path for moving test charge from point A to point B. We have to move this charge on this path and then calculate the work done. What will be the work done? E vector dot dl vector. So we know that what is the value of E vector? E vector here is electric field. What is the electric field on the test charge in moving it from point A to B? So what is the electric field? Electric field, basically electric field is termed as a electric field is connected to the force F vector. F vector is equal to q naught E vector, and this force is acting radially outward. So the force F vector acts on a test charge due to source charge plus q. This plus q charge will act on the q naught force on q naught, which is represented by F vector, and the total work done is given by q naught upon 4 pi epsilon naught r. When we put the limit here ra to rb, distance from ra to rb, so it will give 1 by rb minus 1 by ra. So the whole expression will be the work done from moving test charge from point A to point B will be represented by here q naught upon 4 pi epsilon naught 1 by rb minus 1 by ra. So the actual work done is represented by this equation. So now we have seen here in this diagram on last page, this work done is independent on this path, like path if test charge is moving from this point to this to this to this, so the total path covered from point A to B will be given by this work done. So So we have seen here the important property. Line integral of electric field is always path independent, and this electric field is always conservative in nature. So what is the definition of conservative field? If this E vector dot dl vector will become equal to 0, means the uh, whole path over a closed path. Now we are taking closed path. Closed path in a reference like from moving this point B to A, then A to B. Then A to B will give a reference of closed path here. So closed path is represented by this loop on the integral from A to B. E vector dot dl vector is equal to 0. That means what we have, the line integral of any only static electric field is independent of the path followed. However, the line integral of field due to moving charge is not independent of the path because the field varies with the time. So next is electric potential. Electric potential, you know, electric potential is always scalar in nature. So electric potential is represented by when we divide this work done with the test charge q naught. Like this, q naught will move here and we will get wab by q naught. This wab by q naught is the expression for the scalar potential, or we can say electrical potential. So electric potential is a physical quantity which determines the flow of charge from one body to another body. So electric potential at a point in the electric field is defined as the in term of work done. What is the definition in term of work done? The electric potential at a point in the electric field is defined as work done in moving a unit positive charge from beginning infinity to that point. When we put here rb is equal to infinity and ra is equal to 0, that means this term rb is equal to 1 over infinity. 1 over infinity will become 0. Sorry, rb is equal to r, and 1 over ra, 1 over infinity ra, we have to put here ra is equal to infinity and rb is equal to r. So that means we get q by 4 pi epsilon naught r. That means we have derived an expression for the scalar potential. Scalar potential means scalar potential. So that means we have v is equal to w infinity by infinity b by q naught. This is the expression for the scalar potential. So here q naught is a test charge. So what are the unit of this electrical potential? Electrical potential has a unit, uh, joule per coulomb. Joule is a unit of work done and q naught unit of a coulomb. So joule divided by coulomb means joule per coulomb, and joule is again defined by newton meter. Newton meter per coulomb is the unit of electrical potential. So now from this definition we have to define here uh, 1 volt. What is 1 volt? Potential as a 1 volt. 1 volt is that much electrical potential if we have 1 joule of work done in moving 1 coulomb of charge from infinity to that point in the electrical field. So this represent the definition of 1 volt. Now we come to the electrical potential difference. Basically, what is difference between electrical potential and potential difference? Potential difference is always taken into between 2 points, say a point A and point B. For example, we have derived WAB by Q naught, Q by 4 pi epsilon naught 1 by RP minus 1 by RA, this expression. And if we simply multiply by this term, we will get this term, and multiply RA with this term, we will get this term. This whole term will be the VB, and this whole term will be the VA. So this will give a difference between 2 points, potential at 2 points, VB minus VA. So that means we have an expression for the electrical potential difference. VB minus VA is equal to WAB by Q naught. Therefore the electrical potential and potential difference both are scalar quantities. Electrical potential at infinity is always zero. Electrical potential near an isolated charge, if Q is here positive, then the value of VB minus VA, or we say potential difference, that is represented by delta V, is always positive. If Q is negative charge, then the value of this is negative. So that means potential difference delta V is negative. So what are the CGS unit of potential? CGS unit of potential is stat volt. One stat volt is again defined as same. One arc is the work done and one stat coulomb is the test charge here. So one stat volt is defined as the amount of work done or amount of energy if we taken has one arc to move one stat coulomb charge from infinity to that point. So this will gives the definition of one stat volt. Now we come to the electrical potential due to single point charge. This is very important thing which we are going to derive. Single charge, in case of single charge, what is the value of work done? Same we have to derive work done from infinity W infinity B. So in that case we have Q by 4 pi epsilon naught R. Expression is Q by 4 pi epsilon naught R. Let plus Q be the test charge placed on the here is a plus Q source charge, and here is the plus Q naught which is taken as a test charge. Then force is acting on it along the outward along x-axis. So F is equal to plus Q naught E vector, which is radially acting radially outward. To prevent this acceleration, the opposite force minus Q naught has to be applied on the test charge. So the total work done will be given as a dw q naught. Dw, basically this is the definition of work done. F vector dot dr, here we are taking dr small distance dx, so we are calculating here. So F vector dot dx vector, what is the F vector? Force can be written as Q naught E vector dot ds vector. So we have Q naught E. Now here we have dot product. What is the angle between electric field and dx? Electric field is along x-axis outward, and dx, direction of dx is opposite to Q naught E. That means these are both, so angle between these are 180 degree here. So we have taken here 180 degree. So cos 180 degree is equal to -1. Therefore the value of it is Q naught E dx into -1, that means minus Q naught E dot dx. So what is the value of electric field here? Q by 4 pi epsilon naught x square. We have put here the value of electric field which we have derived. So we have this expression now. So now we have calculated dw. So what will be the total work done? dw is the small work done on this point, moving this point. So we are calculating here from infinity to b, we have to move this test charge on this point from infinity to b. So there will be the infinity to b is the infinity to b. So we have taken here put the value of dw here. So we get q naught upon 4 pi epsilon naught x square. So all these parameters are constant, only x square is a variable. So 1 by x square dx. So what is the integration of 1 by x square dx? Minus 1 by x. सो माइनस माइनस साइन प्लस हो गया। सो यहाँ पे हमने ये एक्सप्रेशन को डिफाइन कर लिया, डब्ल्यू ई नॉट बाई डब्ल्यू इन्फिनिटी पी डिवाइडेड बाई क्यू नॉट इज इक्वल टू क्यू बाय 4 बाय एप्सिलॉन नॉट आर। दिस इज द electric potential due to the single point of charge. So we have derived this expression, V is equal to Q by 4 pi epsilon naught r. Next we comes to the electrical potential due to the group of point charge. Now we have in a different point charge, say we have to derive all the potentials. First of all, we will derive all the potential due to single charge. Then we like at point P we have to calculate the electrical potential. So electrical potential due to Q1 at point P will be represented by V1, due to Q2 will be represented by V2. Then sum of all these V1, V2, V3 up to Vn will gives the total electrical potential at point P. So it can be represented in the form of summation. So 1 V is equal to 1 by 4 pi epsilon naught summation I is equal to 1 to n Qi by Ri. That means V is equal to 1 by 4 pi epsilon naught summation. If we put this value in term of position vector, we have r vector minus ri vector. So that means in term of position vector we can represent this electrical potential in term of position vector. So here we have concluded that electrical potential V is inversely proportional to 1 by R. But previously we have seen in the last chapter Coulomb force, which is inversely proportional to the R square. So here we have V is inversely proportional to the R, whereas Coulomb force is inversely proportional to the R square. Now again we have to think about potential is a scalar quantity, whereas force or electric field is a vector quantity. So this is very important phenomena. So now we come to the important expression, which is the electric potential due to the electrical dipole. First we will derive it on axial line. For the axial line we have now we have to derive this expression. See here we have negative charge at point A and plus charge at point B. At point P we have a test charge plus 1 coulomb. So we have to calculate the electrical potential at point P, and due to this set of electrical dipole, and you know what is the electrical dipole? This is a set of two equal and opposite charge separated by some constant distance. So we have taken here minus q charge at point A and plus q charge at point B, and the difference between these two points we have taken by this L, and you know we have to calculate potential at point P. Now first of all we have to calculate potential due to this plus q charge. So it will be represented by 1 by 4 pi epsilon naught q upon x minus L. So at this point, due to plus q charge, this distance from the origin we have taken as x. So what will be the distance connected to the plus q charge and P? This distance is x, and from the origin this distance is L. So what will be the PB? PB is the OP minus OB. What is OP? X, OB, L. So that means what is the value of PB distance? X minus L. So this will be the 1 by 4 pi epsilon naught q upon x minus L. Whereas now we have to calculate potential at point P due to this minus q charge. So what will be the distance here? AP. So what is the value of AP? OP plus OA. What is OP? X plus L. So that means VP due to minus Q charge is equal to 1 by 4 pi epsilon naught minus Q upon X plus L. Now what will be the total potential? Total potential is the sum of potential due to plus Q charge and minus Q charge. That means we have to add both these terms. So by adding both these terms we get Q by 4 pi epsilon naught 1 upon X minus L minus 1 upon X plus L. We take LCM and what we get here, X square minus L square into 2 dot upper term is 2L. So what we have here, 1 by 4 pi epsilon naught Q into 2L is represented by P. P is a dipole moment. So we have VP. VP means electrical potential at point P due to dipole is the 1 by 4 pi epsilon naught P upon X square minus L square. Now we come to the another case of equatorial line. At the equatorial line, what we have here, we place the charge at this point which is perpendicular. Now we have to calculate here potential at point Q. So now this point Q is connected to minus Q and this point Q is connected to plus Q charge, and here we have a electrical dipole. This is the case when electrical dipole potential. This is the case we have to find out potential at a point on the equatorial line and dipole is placed here. So uh, now we have VQ due to plus Q charge. Potential at this point due to this plus Q charge is represented by 1 by 4 pi epsilon naught Q upon BQ. What is BQ here? We will see later here. So now we come to this point, potential due to minus Q charge at point this Q is 1 by 4 pi epsilon naught minus Q. What is distance here? AQ. So sum will be the Q upon 4 pi epsilon naught 1 upon BQ minus 1 upon AQ. This BQ and AQ will be the same. So that means if this is the same, we can take here value AQ or BQ. So this will cancel out and it will become 0. That means the whole term will become 0. That means the net electrostatic potential at a point in the electric field due to electrical dipole at equatorial line is always 0. So next we come to the equipotential surface. This is the very important part due to examination point of view. What is equipotential surface? Equipotential surface at any point of which the potential due to charge distribution is same. The potential due to charge distribution is same means at every point of the surface have same potential. For example, in case of uniform field, this will form a plane equipotential surface. This equipotential surface will be in the form of plane if we place the charge in the uniform electrical field. So the another case is for an isolated charge. Isolated means plus Q charge is isolated. If plus Q charge is isolated, that means charge is placed here, plus Q charge is placed here, and the potential equipotential surface is created here. These surfaces are always spherical in nature, so these spherical surfaces are called spherical equipotential surface. So spherical equipotential surfaces are created in case of isolated charges, whereas planes equipotential surfaces are created in case of charge when placed in a uniform electrical field. So this is very important thing. So next is we come to the property of equipotential surfaces. Property of equipotential surfaces, these are very important property of equipotential surfaces. Like first property is no work is done in moving a test charge from one point to another. Like if we come VB minus VA, this is the definition which we have derived for the electrical potential difference. So potential difference is represented by WAB by Q naught. If A and B are 2 points on the equipotential surfaces, means these points have same potential. Equipotential means same potential. So if VB and VA both have same potential, that means their difference will be 0. VB minus VB or VA minus VA, it will become, so it will become 0. That means WAB by Q naught is equal to 0. As we know, this Q naught can never be 0, test charge can never be 0. That means this work done from moving point A to B will be 0. So that means we have derived no work done in moving a test charge from one point to another on equipotential surfaces. Then next we come to the electrical field is always perpendicular to the element dl. This is very important property. Electrical field is perpendicular to the element dl of equipotential surfaces. For example, if this work done is equal to 0, that means the work done we can here represented E vector dot dl vector, the line integral from point A to B, the line integral of A vector E vector dot dl vector. So this is a dot product. We can write here E dl cos theta. Theta is the angle between electric field and dl vector. So E dl cos theta is equal to 0, and cos theta, if we know here E never be 0 and dl never be 0, that means therefore cos theta is equal to 0, and cos theta is equal to 0 when theta is equal to 90 degrees. That means cos theta is always 0 at 90 degree. So that means what we have proved here, the electric field is always perpendicular to the element dl of the equipotential surfaces. Now we come to the next point, third point. Equipotential surfaces indicate region of strong or weak electrical field. Oh, this is a very important definition. E is equal to negative dV by dr. So if we come, dr is here, E, if we shift here dr here and E here, that means dr is inversely proportional to the electrical field. So that means equipotential surfaces indicate region of strong or weak electrical field. And when it is strong, E vector is strong, when dr is very small. That means their separation of equipotential surfaces will be very smaller and vice versa. Therefore equipotential surfaces will become very crowded. In case of crowded surfaces, there will be strong electrical field, and in case of if there will be no crowd or equipotential surfaces are very away, that means there will be smaller electrical field. Smaller electrical field means there will be weaker electrical field. So we have proved equipotential surfaces can act as a region of strong or weak electrical field. Next we come to the point 2. Equipotential surfaces cannot intersect. This is very important property. If two equipotential surfaces intersect, then the point of intersection will be two different electrical potential, as we know. The what are the property of electrical line of forces? These can never be intersect. So that means equipotential surfaces can never be intersect. That means then at point of intersection there will be two electrical potential difference, which is never be possible. So two equipotential surface can never be intersect. Okay, so this is a very important. Electrical potential is a scalar quantity, whereas potential gradient, which is known as electric field, which is a vector quantity. And the negative sign of potential gradient shows that this you know already. So now we come to the electrostatic potential energy. Electrostatic potential energy, which is given by, here we have set of two charge. If we multiply a charge with the electrical potential, then it will become work done. So this will be the test charge, as you know, WAB by Q. If we shift Q here, then it will become work done, and work done is always taken as in term of energy. So the work done in moving a charge from point Q to infinity to that point, we will represent here electrostatic potential energy in the form of work done, and it will give the expression U is equal to 1 by 4 pi epsilon naught q1 q2 divided by r2 minus r1, and r2 minus r1 is the distance, this AB. So it can be represented in the position vector form r12. So again we have expression for the potential energy. Now we have three charges, set of charges. So potential energy will be the, this is the important thing, that uh, now here is a point A which is connected to O by distance r1, then point B where q2 charge is placed and connected to O by distance r2, and point C which is placed at a distance r3. And now what we match here, AC, CB and AB. What is the difference? AC r3 minus, if I come to this triangle r, this position vector OA, OC and AC, three position vector are here, and the triangle is OAC. So we have this distance r1, this distance r3. So what is the this distance r3 minus r1 AB. So we have here potential due to AC is 1 by 4 pi epsilon naught q1 q3 upon r3 minus r1 vector. Now we have to calculate potential at point C. Then what will be the potential? Here we have connected point B and point C, and what is the difference? r3 minus r2 vector. So q2 is placed at point B and q3 is placed at point C. So what is the position vector along BC? r3 vector minus r2 vector. So we have 1 by 4 pi epsilon naught q2 q3 upon r3 vector minus r2 vector. That means next third term will be the AB due to potential difference due to q1 and q2. What will be that? r2 vector minus r1 vector. So this will gives this term q1 q2 upon r2 minus r1 vector, and we can write here r12, r31 and r32, these all these terms. So this will gives the electrostatic potential of three charges. So if we have a set of number of charges, and that means the potential energy will be the sum of all these, and it can be represented as in the form of summation. So we have a set of this is the electrostatic potential of energy due to an charge system. So now we come to the area vector for the expression of Gauss law. Gauss theorem is a very important theorem. So first of all we have to define area vector, and then we have to come for the electrical flux. So very important part is that now what is area vector? So area vector is represented by ds vector multiplied by n cap. N cap is a unit vector along ds. So small area of a surface can be represented by vector ds vector. Is this is the magnitude ds, and n cap is a unit vector. So this is the unit vector along this small area ds. So ds vector is represented by ds into n cap, where n cap is a unit vector. So we have represented here area in the form of vector. So area ds represent basically surface area, smaller surface area, and n cap is the unit vector along this ds vector. And electrical flux, we come to the electrical flux. Now electrical flux is linked with any area. Surface area is defined as total number of electrical line of forces that normally passes through the surface. Like electrical flux at point, we have to mention here now, sorry, we shift here. Okay, electrical flux is basically d phi through a small element ds due to electrical field E at any angle theta with small ds. So this is the smaller flux d phi E vector dot ds vector. If electric field is along this direction and ds is the area vector, so what will be the total flux? Total flux is the summation over integration over s over a closed surface. So these surfaces must be closed. So E vector dot ds vector integral over s. So it will become E s cos theta or E vector dot ds vector. So as we know that electrical flux is a scalar quantity, and but it is a property of vector field. So electrical flux is a scalar quantity, and the what are the unit is the electric field multiplied by area. So its unit as Newton per coulomb dot meter square or Joule meter per coulomb. So next we come to the point, their special case, when it will become positive, when it will become zero, and when it will become negative. When theta is less than 90 degree, flux is positive. When theta is equal to 90 degree, that means E ds cos 90. What is the value of cos 90? 0. That means in that case flux is always 0. When theta is lies between 90 degree to 180 degree, that means we have value of flux is always negative. So now we come to the solid angle. Solid angle is a three-dimensional equivalent to the two-dimensional plane angle. We will discuss it later on. And now we come to the Gauss theorem. Gauss theorem is a very important theorem. And what are the property of Gauss? What are the statement of Gauss theorem? Statement of Gauss theorem is statement of Gauss theorem is important. The surface integral of electrical field intensity over any closed hypothetical surface, and that hypothetical surface is called Gaussian surface in a free space, is equal to the 1 by epsilon naught time of net charge enclosed within the surface. So now we are defined, this is the mathematical definition for the Gauss theorem. Phi E is equal to E vector dot ds vector over any closed surface S. So this is 1 by epsilon naught time charge enclosed within the surfaces. Now we come to the proof of Gauss theorem. Here we have represented a solid angle, and that is we have taken a Gaussian surfaces here ds vector is a area vector here, and r is the radius of this sphere. So E vector, so this will gives you E vector 1 by 4 pi epsilon naught q by r square into r cap, and this is the definition of area vector which we have defined in the later slide. ds dot ds n cap. So now from this expression we have 1 by 4 pi epsilon naught q ds by r square r cap dot n cap. What is the angle between this r cap and this n cap? R cap is a basically here we have taken a unit vector. So what is the angle between here r cap and n cap? N cap is taken here, so angle is here we have taken 0. So the value of r cap and n cap both are unit vector and angle is 0. That means the value of r dot r cap dot n cap is equal to 1 unity, or we can say unity because it is a form of unit vector. So we have taken a its value is equal to 1 because angle is also 0 degree. So 1 into 1 multiplied by 1 into cos 0 degree, this is will be equal to the 1. That means the value of this is equal to 1. So d phi is equal to 1 by 4 pi epsilon naught q ds. So value only value depend upon this ds. So now we come to the total electrical flux. Total electrical flux is the integration of d phi. Integration here we have taken as a closed loop. So this will give we have put here value of d phi 1 by 4 pi epsilon naught q by r square integral over s into ds. What is the surface area? 4 pi r square. So we have put here value 4 pi r square and it will become to the 4 pi r square is cancelled with the 4 pi r square and it will only remain q by epsilon naught. That means we have proved here phi e is equal to q by epsilon naught. So this will be the again definition of what we have stated mathematically here. Definition of Gauss law, or we can say Gauss law in electrostatic or Gauss theorem in electrostatic. And that means the total electrical flux is always 1 by epsilon naught time of charge enclosed by a closed surface. So hope you understand all these parameters. What we have now, I am going to summarize what we have discussed here in the presentation. We have defined line integral of electrical field. Then we had done expression for the electrical potential and potential difference. Then we come to the point electrical potential due to single point charge, group of charge and electrical dipole. Then we had done what are equipotential surfaces and their properties, and then we have defined the expression for the electrostatic potential energy and area vector, solid vector and electrical flux. After that we have done the proof of Gauss theorem and its application. Now we come to the Coulomb's law from the Gauss law. This is again a very important thing, I think so. Deduction of Coulomb law from the Gauss theorem. So this is very important part, deduction of Gauss. Now we have taken a Gauss law, definition of Gauss law. So definition of Gauss law is E vector dot ds vector is equal to q by epsilon naught over closed to a surface S. So E vector dot ds vector represent the electric line of forces over closed surfaces S. Now if we put here, basically this represent phi E. Phi E means flux, electrostatic flux we can say, or we can say electrical flux. So if I integral over s ds here, so E into 4 pi r square surface area of this sphere, and electric field is taken again along this side, and ds is a area vector which is taken along the electrical field, and this what is the whole surface area of this that is 4 pi r square, and this 4 pi, and then we have put this value of ds 4 pi r square and rearranging the term this 4 pi r square come to here, and we get E is equal to q by 4 pi epsilon naught r square. And if the charge q naught is placed at a point where electric field is calculated, and from the electrical field we can calculate the force, because we have a relation F is equal to q naught E, where q naught is a test charge. So q naught here, what is the value of E? Q upon 4 pi epsilon naught. So it will become F is equal to q naught upon 4 pi epsilon naught r square, or we can say 1 by 4 pi epsilon naught q into q naught by r square. This will represent a Coulomb law. What is the statement of Coulomb law? Force is directly proportional to the multiplication of test charge and source charge, and inversely proportional to the distance between the source and test charge, square of the distance between the source and test charge. So this will gives the definition of Coulomb's law, which is deducted from with the help of Gauss theorem. This is again one of the important theorem. So hope you understand all these concept of this. With this I finished my presentation, and thank you all.